We are on example 7c in section 2.3. I mentioned yesterday that this was going to be similar to a multiple choice question. This one and D, both of them. And the only rule that we know now for differentiation, besides the actual limit definition, right, is the rule, what's it called? The starts with P, ends with our. Power rule, the power rule. So remember the power rule, we have to have everything written in the form a times x to the n, right? And we know that if there's multiple terms, we can keep going, right? So can we use the power rule on this the way it's written? No. Can we just take the derivative of the top and the derivative of the bottom and divide them out? No. Unfortunately, if you have y equals f over g, then y prime, unfortunately, is not in general equal to f prime over g prime. That's a quotient rule, and we're going to learn that in the next section. So what we have to do is somehow rewrite this so that we have multiple terms that are all of this form. Anybody have any kind of algebraic way to accomplish that? Ratcon. I like it. That doesn't work. I do like Ratcon, though. I'm not going to lie. Direct substitution. Wow. Vertical asymptote. I don't know. Just random math things. What? We could do that. There's two ways to accomplish that. Yeah, I'll do it the Kaz way first, which is not the way I would do it. But since he volunteered it, if you bring that to the top, it's going to be x to the negative 1/2. And I guess instead of dividing by 2, we can multiply by 1/2. So if you do something like that, now you have a product. Now, unfortunately, if you have y equals f times g, then y prime is not equal to f prime times g prime. You can't just take the derivative of each of them. But what we can do is what? You can distribute. And if you do that, it'll be fun. Now, that's not the way I would do it, but it will work. So if you want to continue with that method, it's the same thing. And this is one of our strategies that we're going to use pretty much all year long. You can split up terms in the numerator by putting each of them over the entire denominator. That works, okay? You can't split up denominators, but you can split up numerators. Martin, did you suggest that from the beginning? Okay, I didn't hear that. You are sitting in the back. Okay, so let's do that. Now, we're not going to take the derivative, so we're going to call it y equals. So we got 2x cubed over, now 2 square root of x, I'm not going to leave it as 2 square root of x. I'm going to call it 2x to the 1/2, because what we're going to do on the step after this is simplify, and we can use the rules of exponents. So the next one will be minus 3x squared all over 2x to the 1/2, and then plus 7x over 2x to the 1/2, and then finally plus 5 over 2x to the 1/2. Now notice what we've accomplished there is we've split it up into 4 individual terms. But there's still work to do yet before we BOTC, bust out the calculus. So we're still going to call it y. As we go through and rewrite each term, we'll simplify numbers and we'll combine the x's. So here the 2's divide out. And we get x to the, what's the rule when the bases are the same and you're dividing? What do you do with the exponents? Subtract them. Good. So we get 3 minus 1/2. Well, that's 2.5. But 3 is also how many halves? 6. So really 6 halves minus 1/2 is 5 halves. Okay, 5 halves, 2.5. We'll prefer to work with the fractional exponents. The next one, we'll just leave 3 halves as the coefficient, and then off to the side, which remember is really in the numerator, we get 2 minus 1/2, which is 3 halves. Plus, then we get 7 halves, x to the 1 minus 1/2, which is 1/2. And on this last one here, we're going to have a 5 halves. There is no x in the top, so you can either think about it as x to the 0 and then subtract, or simply just say, well, I'm going to slide that to the top and change its sign. Either way, you get negative 1/2. Now, as you go through here, we have 4 terms. Are they each in the form a times x to the n? Yes. So now we are finally ready to bust out the calculus. So don't forget the all-important left side. This is the noun format where we have a function equaling to something, so we got to take the derivative of both sides. What becomes of the left side? Y prime or dy dx. And now here's the fun part. 4 terms, that's 4 tiny little problems all in one. We just go down the line one at a time. We'll do the first one first. That makes sense. From left to right. What's the derivative of x to the 5 halves? 5 halves, because it's really a 1 there, times x to the 5 halves minus 1, which is 3 halves. Yes. Good. We go on to the next one. We got negative 3 halves times the exponent 3 halves. That gives us negative. We multiply straight across, right? 3 halves times 3 halves, so it's 3 times 3 over 2 times 2, which is negative 9/4. We multiply. And now we subtract. 3 halves minus 1. That's minus 2 halves, so that's 1 half. We'll get used to working with fractions. And then plus 7 halves times 1 half is 7/4. X to the 1 half minus 1 is negative 1 half. And then the last one, 5 halves times negative 1 half is negative 5/4. X to the negative 3 over 2. Right, we subtract 1. Negative 1 half minus another 1. Wow. So lots of fun with fractions there. I told you this would be a multiple choice question. That probably would not be the answer choice, because I'd do one more thing just to keep the fun going, right? It's like an extra day at Disney World. And who doesn't want that? All right. How long does your Disney withdrawal last when you leave?
Oh.
Mine lasts like a month or two. It's just like you go to the store and you buy something, and the person is not rude or anything, but they're not exceptionally nice, and you walk out and like, what's that guy's problem? You know? Because at Disney World, it's just like, wow, they know how to do it. So mine usually lasts for a couple months. Yeah, I'm just sorry. Let's go ahead and get rid of the negative exponents and put it back into radical dude format, okay? So the 5 halves is cool, but then the x to the 3 halves puts it back as, is it the square root of x cubed or the cube root of x squared? I don't know. Square root of x cubed? Yeah, you're right, yeah. Because remember, the denominator is the root, right? Because they grow in the ground in the denominator where the roots are. Oh, yeah. Minus 9/4. X to the 1 half, that's the square root of x, right? And then, we got a negative one here, so this is fun. I got a 7 in the top, I got a 4 in the bottom. Guess who's going down to join the 4? Square root of x. Excellent. And then I got a minus 5 over 4. Coming down with the 4, you're going to have another cube root of x squared, but now in the denominator. And that right there for this test is what the answer choice would be. So there are lots of tiny little opportunities for success, but there's also lots of little tiny opportunities for careless mistakes. So did I do it wrong? Yeah, see, look. So guess what an answer choice might be? This. It might put it as A, right? What did I not do? I didn't mentally run through the tape at the end of the race. So learn from my mistakes, right? I ran the first 26 miles of the marathon, but the last 0.2, I'm just like, I'm good. Okay? You got to finish all the way through. And I did. And I was thinking about Disney World again. And yeah, sorry. That would be the square root of x cubed, yes? All right. And that would be, let's say, answer choice, right? When in doubt, C. So I'd make that C, because I like to reward y'all when y'all don't know what you're doing. So. No. All right. So can y'all handle a problem like that? Yes, with a little practice. Where do you go to practice? Worksheet, right? Yeah. Now, let me show you another thing that we're going to do with that in the future. And by in the future, I mean like right now, but not on this test. The whole purpose of taking the derivative is so that we can use it. And this right here is not a very useful version simply because, you know what we end up doing with the derivative? We end up setting it equal to 0. Now, how easy is that to solve algebraically? Right? No. So there's another thing that we can do, and it's called factoring out least powers. So let me show you what that's going to look like. Factor out least powers. All right, so from this step here, I'm going to have y prime equals. Let's go ahead and look at the numbers first. Is there any number that I can factor out? What's the smallest magnitude of the coefficients? Which one's the smallest? Well, without the plus or minus, we have 5 halves, which is really 10/4, 9/4, 7/4, and 5/4. Which one is the smallest? 5/4, right? So let's go ahead and factor out the 5/4. So we look for the magnitude of the coefficients. But when we're looking at the x's, we actually look at the exponent itself. Which exponent is the smallest, including positive or negative? Negative 3/2. Good. Negative 3/2 is the smallest exponent we have. Okay? We are then going to factor out that least power, which is negative 3/2. Now, when we do that, I like to put the beefy bracket because that implies that we're serious, right?
Is it a coincidence that they're both on the same?
Yes, it is a coincidence that they happen to be on the same term. That's not always going to necessarily happen. Right. Yeah, we can pull that least power from any term. We can pull the common multiple from any term. They just happen to be on the same term here. Now, if you factor out the least power and you pull out the smallest coefficient fraction, what should end up here is going to be lovely. Okay? And by lovely, you'll see what I mean. Ramos, you're curious, right? What does lovely mean in terms of this? All right. Let's do it. Now, here's the idea. When you factor something out, what process is it? What operation? Add, subtract, multiply, divide when you factor something out. You're dividing something out, okay? So I want to factor out or divide out a 5/4, first of all, from a 5/2. So if you imagine that we're dividing it like this, if you were to simplify this expression right here, what would you get? What is 5/2 divided by 5/4? 5/2 divided by 5/4. Stay, change, flip, right? That's 5/2 times 4/5. Your 5s would divide out. You're left with 4/2, which is 2. Now look what happens. Let's check real quick. Distribute it back in. What's 5/4 times 2? Well, it's 5/2. So yay, it worked. Now let's do it with the x's. When we're dividing out, what do we do with the exponents? Add, subtract, multiply, divide. Subtract. Yeah, subtract, right? So what is 3/2 minus negative 3/2? 6/2, which is 3. Lovely. Lovely. Let's do it again. Okay? Now we're going to go to the next term. What is, I know it's going to be negative. I'll get that out of the way. What's 9/4 divided by 5/4? Well, that's 9/4 times 4/5. Your 4s divide out and you're left with 9/5. Sweet. Or no, that's wrong. Yeah, 9/5. That's good. Right? Let's see. If I multiply it back in, my 5s divide out, I'm left with 9/4. Yeah, perfect. Now it's the x's that work out. What are we left with the x? 1/2 minus negative 3/2. What we started with minus what we factored out. 1/2 minus negative 3/2 is 4/2 or 2. Lovely. Plus, what's 7/4 divided by 5/4? 7/5, right? Stay, change, flip. The x's now, let's see what we get on the x's. I got a negative 1/2 minus a negative 3/2. That's really negative 1/2 plus 3/2, which is 2/2, also known as 1. Lovely. And then finally, this one's easy. If I factor a 5/4 out of itself, I get 1. And what's negative 3/2 minus negative 3/2? We get x to the 0, which is this. So notice we end up with a nice little whatinomial in there. We get a polynomial. If you factor out the least powers, you should end up with nice coefficients. Now, why is this even any better? Well, look how lovely this becomes if I simply rewrite it. I'm going to have a 5 and a 4. That x to the negative 3/2 now being a factor, I can throw it back to the bottom and call it x cubed, and I'm left with 2x cubed minus 9/5 x squared plus 7/5 x minus 1. And I can even distribute the 5 back through in the top to get rid of those fractions. But notice now, if I have a ratio, now it's pretty easy to solve when you set it equal to 0, or easier, because a fraction is equal to 0 when the numerator is equal to 0. And now I'm just setting a cubic polynomial equal to 0 instead of this wacky, funky thing. So there will be a time where we do that. I just want to show it to you now because you probably haven't factored out with fractions before. But we're just dividing, which means we're just subtracting exponents. So on this next test, I will not have that as the answer choice. I will have this. Just simplify each term. So this is, wow, this is quite the problem, huh? Yeah. Lots of fun there. Okay, look at this one. This one is also going to be a multiple choice question. We're trying to find the derivative of that function. Right now I look at it and it looks like it's the product of two variable functions. Can I just take the derivative of that and the derivative of this and do something with that and just write down anything? No. I have to be able to write it so that it's multiple terms and they're all in the form ax to the n. So any ideas algebraically how we can do that? Think. Sledgehammer. Yeah, let's just hit it with a little sledgehammer, which of course means expand it out. That's all that means, right? Now, can I distribute the x in there first? No, your dear Aunt Sally says no, no, no. Right? Please, so we look in the parenthesis, please. Nothing to do there. Excuse, exponent, we'll do that. How do we square a binomial quickly? Square, multiply, double square. We square the first, 3x quantity squared is 9x squared. To get the middle term, we multiply those to get 6x and double it to get 12x. And then we square the last, 2 squared is 4. And now I can distribute the x because that's multiplication. So we get 9x cubed plus 12x squared plus 4x. And oh my gosh, I've worked hard, I'm tired. That must be the answer. Right? I've done some math. That must be the answer. That would be an answer choice on the test. What have we forgotten to do? Take the derivative, right? Bust out the calculus. Let's get the good stuff going here, the calculus. What's the derivative of the left side? Y prime, right? Or dy dx. I'll keep coming back to that. I like that one. And then term by term, we got 3 terms, so we'll have 3 terms coming in the derivative, and the first one becomes 27x squared plus, I forgot something, what did I forget? X times, yeah, this is because these look like terms. X times 12x is 12x squared. Thanks for catching that, guys. Hey, it's not only BK Moldy Cheese Cheerleading Tool Day, it's Friday. Okay. So what would this middle term become then? 24x, and then the 4x becomes 4. Yeah. And that's the derivative, right? So that type of problem is a little bit easier than the other type. So, but I guarantee you'll have one of each of those on the next test, and they'll both be multiple choice questions. So expand and then split up. What's that? You can always do your best. That's right. Did you say do your guess? Do your best. Your best guess? Again, you're in the back. I can't really hear. Right. When in doubt, you always want to do your best, even if it's just guessing randomly, haphazardly. Make it your best haphazard, random, shot-in-the-dark guess. All right. A powerful application of the derivative is finding the values of the function where it has a horizontal tangent line. Why is a horizontal tangent line so important? What is the slope of a horizontal line? 0. Yeah. So here's why it's so important. If you have a function as simple as that, we might be interested in finding this value of x or this value of x. Because if we're modeling something in the real world that behaves according to that, this would be where we're at a relative maximum level, whether it's cost or profit or temperature. And this would be where it's at a minimum, a local minimum. And so how do we find those values of x? There's no explicit equation like there is for the vertex of a parabola, but we do know that the slope of the tangent line at those points is 0 because they're horizontal lines. So what we can do then is we can find the derivative of that function, and instead of plugging in an x and finding the slope, we can set the derivative equal to our desired slope and do what? Solve for x. Yeah, let's give it a try. Find the coordinates, x, y, that's the ordered pairs, and the equations of any horizontal tangents to this curve right here. All right, so what's my plan of action here? I want to find where we have horizontal tangent lines. Now I'm getting nervous. Find the derivative, right? Because the derivative will give us the slope at any point, and then set it equal to what? 0. Yeah. And here's just a little tip throughout the year. If you're ever doing a problem and you don't know what to do, and it's not a limit, because when it's a limit, when in doubt, DNE, right? But if you have an equation, when in doubt, take the derivative and set it equal to 0. Because a lot of the times you'll be right, because we do that a lot. Because, again, we're after these values of x. So let's do that. We'll take the derivative. We have 3 terms. Do any of them need to be rewritten? No. So y prime would equal 4x cubed minus 4x plus 0. Now, you always have to show the equation that you're solving, so you do need to make sure that you're showing that you're setting it equal to 0. Now the calculus is over, really, and it turns into an algebra problem. How do we solve an equation once it's equal to 0? We attempt to factor it. And the first rule of factoring is to Google it, right? No, we look for a common factor first, and then we Google it. What's common? We factor out the least powers. I see a 4, and which power is smaller, 3 or 1? 1. So we've done this with nice integers. Now, when you do 4 divided by 4, what do you get? 1. And what's the rule? When you're dividing, what do you do with the exponents? 3 minus 1 is 2. So we almost do that instinctively when we have nice positive integer exponents. It's the same thing we did with the fractional ones, though. And then minus 1. Make sure you keep it a 0, equal to 0. Now, from here, it's perfectly fine if you can write down the solutions without going any further. You could just say x equals, whatever. How many solutions would we have, though? 3. As long as you know there's 3, you can go for it. But some people kind of miss 1. If you need to keep going, x squared minus 1 would be x minus 1, x plus 1. It's the difference of squares. So x would equal, some people forget this one, right? That one is often overlooked. That's going to have a solution of what? 0 and then 1 and negative 1. What about the 4? Did we put 4? No, because 4 is a constant. Is 4 ever going to equal 0? No. What if it went as at Halloween as a 0? The 4 dressed up like a 0. Would it be a 0? No, it's still a 4 on the inside, right? The clothes don't make the man. So some people always want to include that constant as well as part of the solution. No. We're trying to find the variable values of x that when you plug them in, give you a 0. All right, so those are the 3 x values where this function happens to have tangent lines that are what? Horizontal. Okay, so now we're trying to find the coordinates x, y, and the equations. So we have half of each of the 3 coordinates. So let's go ahead and list the points. The first point's going to be 0, comma, f of 0. The next point's going to be 1, comma, f of 1. And the last point's going to be negative 1, comma, f of 1. How do we find the y values? Plug them back into where? Y prime or y? Y, good. Now, if we plug a 0 in, that's pretty easy. We get, what? 2. 0 minus 0 plus 2 is 2. Sweet. If we plug in a 1, that's not so bad. We get 1 minus 2 is negative 1, right? Plus 2 is 1. Now, if I plug in a negative 1, I get the same thing, right? The reason I get the same thing when I plug in a negative or a positive number, any x really, is because the only 2 variables that are there have what type of exponents? Positive, but they're also even exponents. So this function ends up being an even function because the rule is if f of negative x equals f of positive x, it's going to be an even function. And it is, because our 2 exponents are both even numbers. What type of symmetry does such a function have? Y-axis symmetry. Okay, that's cool. I know it has y-axis symmetry. So now to finish up the question, I need to find the equations of the tangent lines. What is the equation of a horizontal line? It's just the form y equals. You don't even have to use Taylor form. You can just say y equals. Now, what would be the equation of the horizontal line that passes through the point 0, 2? Y equals 2. Very good. And, of course, the one that passes through the point 1, 1 would be y equals 1, and then y equals 1 again. Same line, but tangent at a different point. It has to be the same y value that the point is. Now, notice just with this little bit of work, and recognizing that it's an even function, we could sketch this graph pretty accurately. I have 3 ordered pairs that I can graph. I have the point 0, 2, and then I got the point 1, 1, and negative 1, 1. Now, one last thing that I need to do is check what is the limit as x goes to infinity of this function. Remember, as x goes to infinity, you really only need to look at the leading term. What happens to x to the 4th when it goes to infinity or negative infinity? What's infinity to the 4th? Infinity. What's negative infinity to the 4th? Infinity. So what that means is if both end behaviors are positive infinity, that this graph comes in from the top, hits that horizontal tangent line, comes up to there, hits that horizontal tangent line, comes down to there, and then goes up like that. And that function has y-axis symmetry. So it looks like a rejected Whataburger logo, right? Somebody was like, no, I think our logo should have cusps at the turns. All right, so not much work, but we get a nice result. All right, so horizontal tangent lines. All right, so let's move on to the next type, and we've had a problem like this. It's important to remember that at any point of tangency, x equals c, at any x value, the function f of x, the graph, and its tangent line, which I'm going to call t of x, t for tangent line, also t for Texas, right? I think they're playing right now, game 2. Anyone with an update? The Astros start soon, too. They play at 2, I think. They start at 2. And the Rangers started, I think, at noon. Yes, you have an update. Oh, C, okay. No, thanks for keeping it real here. No, C is just at any x value. So at any particular value of x, the function and its tangent line share 2 things. They share a y value, and they share a slope value. Okay? So if you have a function that looks like that, and you have a tangent line right there, this is x equals c. That function, f of x, and the tangent line, which I'm calling t of x, they share a y value, right? And they share a slope value. Yes, Cole? 3 to 4? Oh, the Rangers are down by 1. In the 7th? Still time. Still time. They got game 1, so every visiting team has won so far, right? Example 9. Here's a nice application. We had one like this on a previous worksheet, but I didn't kind of talk you through it. I was letting you kind of figure it out on your own. So many people just looked at the key and said, okay. I think we might have gone over it. But this also, I guarantee, will be a multiple choice question on your test. Very similar to it. Find the value or values of k such that this line is tangent to the graph of this quadratic. Find the value of k so that that tangent line is tangent to that parabola. Now, the k value that we're finding, notice, is only existing one place. It's the linear coefficient of my quadratic. How am I going to start a problem like that? Well, I know that at the value of x where it's tangent, the 2 functions are equal and their slopes are equal, which means their derivatives are equal, right? If their y values are the same, then f of 1 has to equal f of 2. And if their slopes are the same, then f prime of 1 has to equal f prime of 2. Yes? This gives us a way to establish a system of equations. So let's do that. Now notice this line is not solved for y, is it? Let's do that first. Red Rover, let 5x come over. There he is. Y'all still play that game ever? No, I wonder if they have like a virtual game, like you could get an app like Red Rover game. You can play it on the iPad. There's the equation of the tangent line. Here's the equation of the function. It's already solved for f. So let's go ahead and force the y values to equal each other. I'm going to set negative 5x minus 9 equal to 2x squared plus kx minus 1. That's setting the y values equal to each other. Now, unfortunately, we can't do much with that equation because it's one equation with how many unknowns? 2. And it doesn't have a unique solution. You always need as many equations as you have unknowns if you want a unique solution. So what else could I do? If their y values are equal, what else is equal? Their slopes or their derivatives, yeah. So let's go ahead and find the derivatives of each of those. And we'll set y prime equal to f prime. Now what is y prime? What's the derivative of negative 5x minus 9? Negative 5, right? Or you can just say, oh, it's a line with a slope of negative 5 everywhere. Or you can use the power rule. So negative 5 is going to equal f prime. Okay. If k is a constant, what's the derivative of f prime? Or the f, sorry, what's the derivative of f? What's the derivative of 2x squared? 4x plus k is a constant, so the derivative of k times x is just k, and then the minus 1 goes to 0. It's a constant. Now we have two equations with two unknowns. And all we have to do is solve that system of equations. And we can use elimination, we can use guess and check, we can use substitution, Kramer's rule. What do y'all want to do? The elimination method sometimes is very, very convenient, but notice this one has like a squared term in it and this one doesn't. So I would probably opt for substitution. Yeah. And looking, I would probably solve the second one for k. I probably wouldn't solve for x on either one of them because there's more places to plug in. But if I solve this one for k, let's see what we get. K would be equal to negative 4x minus 5. And what I can then do is come over here to this other equation and plug in for k right there. And we have to be careful, right? So here we go. Negative 5x minus 9 equals 2x squared plus parentheses. K is negative 4x minus 5 times the x and then minus 1. So that's just the substitution right there. Oops. Substitution. Now I have one equation with one unknown. We just got to solve for x. Should we still be careful or should we just start being a little bit careless at this point? Go crazy. Okay. In a good way, though. I would expand it first. Now notice this one, we do have to distribute the x, and it's on the right-hand side. We're not used to doing that or seeing that, so just be aware of that. And there's a plus sign here, so that's not minus. If that were minus, we'd have to distribute a negative as well. This just becomes minus 4x squared minus 5x, and then minus 1. And now I'm noticing that I have a squared term, a couple of them, non-squared term, and a constant. So that's going to end up probably being a quadratic. And, of course, how do we solve quadratics? Get everything on one side, set it equal to 0. And then we're going to try and factor it. So I'm going to go one last step here before I collect, because I can combine those two terms and get negative 2x squared minus 5x minus 1. Now, if I want to factor, I also want my leading coefficient to be positive. So what I'm going to do then, since my x squared term is currently negative, I'm going to bring everything over to the left side, just so that this leading term is positive. So here's where you can kind of make some careless mistakes. So the more lines you show, you know, the better off you are in avoiding those careless mistakes. Now when I bring the negative 5x across, it cancels with that negative 5x. So, and when I bring the negative 1 across, it becomes negative 9 plus 1, which is negative 8. And, of course, now it's 0. And I think now we can go crazy. Yeah, if we factor it, we factor out of 2, we get x squared minus 4. And at this point, you can write down the solution or solutions But remember, there's how many? Well, let's see. Let's keep going. X squared minus 4 is the difference of squares. So really, there should just be 2 and negative 2. It looks like there's 2 solutions. Yeah. Because the 2 in front, remember, even at Halloween, wouldn't be a 0. We're just looking for the variables. Now, if this were a multiple choice question, you've done a lot of work, right? You've done quite a bit of algebra here and a little bit of calculus. Answer choice A might be 2 or negative 2. It might be one of those two. Is that the answer? Is either one of those what we're looking for? Yeah, very good. So don't take the bait. Make sure you're always answering the question. We're trying to find the value of k. Now, because I have 2 values of x, here's the nice thing about substitution. That thing that you substituted in right there, it's already ready to go solve for the value that you need of k. So when x is equal to 2, we get k is equal to, well, plug in a 2. You get negative 4 times 2 minus 5, which is negative 13. So there's one of the values of k. But when x is negative 2, we get k equals negative 4 times negative 2 minus 5, which ends up being positive 3. So there's a couple ways that I could put that as a multiple choice question. I could either only put one of those as an answer choice, not both, I wouldn't put both, or I can turn that into one of those multiple choice questions. Which of the following are solutions? I could put like Roman numeral I is k equals that, Roman numeral 2, k equals 3, Roman numeral 3, k equals pi or something. And then, of course, the answer choices would be I only, I and I, you know, something like that. That would not be very fun, or it would be? Save it for a free response? Well, anyway, we found both values of k. Now, what the heck did we just find? Well, let me show you. If we were to plug this negative 13 in right there for k, or this 3 into k, we're going to have a quadratic. We'll have 2 quadratics, and the same tangent line, this is a fixed line, should be tangent to both of those quadratics at 2 different x values. I took the liberty here of showing you what the result is. All right, so the left one is with the k value of negative 13. We get this parabola, which looks like this one. Here's the tangent line that we talked about. It's fixed. Notice it's the same on both. It's tangent to this parabola at 2. And if I let k equal positive 3, we get a parabola still that opens up, but it's shifted over. And the same exact line is now tangent to that parabola at a different point, namely 2. So that's essentially what we did. We found the 2 parabolas that were tangent to that line. And we also found the x values where it happens. Could we then write the equation of that tangent line? We could, or we can just say, hey, we already have it. Yeah. All right. Can y'all do a problem like that? Heck yeah. Okay, of course you can. Really all we did was this. We solved for y, and we set the 2 functions equal to each other. We took the derivatives of both and set those equal to each other, and then we solved the system. There's a lot of algebra in calculus. Now, I wish we had time for the sine and cosine rules, but we don't. Or do we? It's Friday. We don't, or we do? I'm just going to throw it in here, but we'll start there again on Monday. I just want to give you something to leave with on this wonderful stinky tool day, okay? The derivative of sine is, guess what? It's cosine. The derivative of sine is what? Cosine. Okay. Guess what the derivative of cosine is? Sine would be a great guess, but no, it's, in fact, negative sine. The derivative of sine is cosine, but the derivative of cosine is negative sine. Now, here's something that's going to help you the rest of the year. We're going to memorize the derivative of all 6 trig functions and all 6 inverse trig functions. Any trig function that starts with co or inverse co, like arc cotangent or inverse cosecant, they're all going to be, guess what? Negative. If it starts with co or inverse co, it's going to be negative. If it doesn't start with inverse co, it's going to be positive. So that will help you. So the derivative of cotangent is negative something. The derivative of cosecant is negative something. The derivative of an inverse cotangent is negative something. All right, so that should help you as we move forward. We're done. We're done for the day.